In this first question, we're asked to find the derivative of this function, dy dx. So notice that the second term is in a non-differentiable form. First term is fine, so let's start by fixing the second term. So leaving this as x to the 5 over 3, bringing the x term to the top on the second term to make it 10x to the negative 4. This is now in a differentiable form, so we can go straight into using the power rule. So dy dx equals, so bring the 5 over 3 in front, reduce the power by 1. So when you're taking 1 off of this, you've got to think of that 1 as being 3 over 3. So it's 5 over 3 minus 3 over 3, which would be 2 over 3. Same rule, power rule for the second term, multiply by the power, which is going to make a double negative to give you a plus 40x. Reduce the power by 1, so it goes down to minus 5. You could then put that back as a positive power. So the first term's fine, 5 over 3x to the 2 over 3. Second term, we're going to make 40 over x to the power of 5. That's as far as that one can go. Question 2, we're given these 2 points and we're asked to find the equation of the perpendicular bisector line of those 2 points. So remember, perpendicular bisector means 2 things: perpendicular, right angled, and bisector, which is another way of saying midpoint. So we need to find the midpoint, the gradient, and the perpendicular gradient. So it doesn't matter necessarily in the order in which you do things. I'm going to start by making the gradient of this line, P to Q, just using the normal gradient formula. So I'm going to do 6 minus 0 over minus 2 minus 10. You've got to keep track of your negatives in this question. So 6 minus 0 is 6. Minus 2 minus 10 is negative 12. That would simplify to negative 1 over 2. Remember, that's not the gradient we need. It's the gradient of the perpendicular to this. So the perpendicular gradient, if you want to use this little notation, remember the 2 gradients, if they're perpendicular, multiply to make negative 1. So it means that the other gradient, the perpendicular gradient, would have to be 2. Okay, so we've got a gradient, still need a point. The point is going to be the midpoint of these 2. So you could use, if you wish, the midpoint formula, or you can do it just by eyeballing them, or, informally. So you're just adding these together and divided by 2. So minus 2 plus 10 is 8, divided by 2 is 4. 6 plus 0 is 6, divided by 2 is 3. So that should be the midpoint for 3. So that eyeballing it like that and doing it informally is essentially just what the midpoint formula says anyway. So now we can use the straight line equation, y minus b equals mx minus a, and just plug in our values. So we get y minus the b value, which is 3, equals the gradient 2, x minus the a value, which is 4, and then just tidying up the algebra. So y minus 3 equals 2x minus 8, giving us a final answer of y equals 2x. Add in the 3 to both sides, so minus 8 plus 3 is minus 5. That's the final answer for question 2. In this question, we're being asked to solve this little log equation, and to be honest, log equations don't really get much easier than this. We can combine these 2 log terms into one, keeping in mind the fact that we've got a negative in between. There's no numbers in front, so we don't need to bring anything up onto the powers. So we're good to go straight into that log rule that says that we could make this into log base 5, and then we're going to divide the x by the 3 just because of the minus, so that becomes log base 5 x over 3 equals 2. Now the goal is to get rid of the logarithm, and you can either do that by introducing a log on the right hand side and then cancelling the logs, or my preferred method is to rewrite this as an exponential. You need to know how to do that. And essentially it becomes x over 3 equals the base number 5 to the power of 2. If you introduce a log on the right hand side, you'll end up with the same answer. Then we just need to solve that equation. So x over 3 equals 5 squared, which is 25. Multiplying both sides by 3, and you'll get x equals 3 times 25, which is 75. Just to quickly show you the other method for this, so you could write this as log base 5 of x over 3, and then on the right hand side, if this is the method you've learned, it would be log to base 5, 5 to the power of 2, like this. The thing there is you've got to remember to write the 5 twice, then you would just cancel the 2 logs, and that takes you back to the same place that we were here anyway. So x equals 75 is the solution for that question. In question 4, the first thing we need to do is to find the missing side of our triangles. So I've separated the triangles into 2, but it was 1 on the original diagram. If you notice that this triangle has got a dimension on the long side, the hypotenuse of 5, this one's 4, that means that that one's 3 by that well-known 3, 4, 5 Pythagorean triple triangle. So you could work it out using Pythagoras, but if you did, that would just come out to be 3. And on the original diagram, these are connected, they're the same length, so that one's 3 as well. This one we'll need to work out by Pythagoras because those are not known numbers. So if we call that side C, then C would be equal to the sum of the squares of the other two sides, and then we're going to square root that. So that's going to be the square root of 9 plus 36, which is the square root of 45. That would simplify down using surge, so that becomes root 9 root 5. Square root of 9 is 3, so that becomes 3 root 5. So that side length there is either root 45 or in its simplified form, that's going to be 3 root 5. So in question 4, part A, part 1, they are asking us to work out the quantity cos p. So cos p we can just work out from SOHCAHTOA. So picking out the triangle that's got the p in it. So remember in SOHCAHTOA, cosine is adjacent over hypotenuse. Be careful with the orientation here. So this is adjacent, this is hypotenuse. So that's just going to be 3 over 5. So no real magic there, just using SOHCAHTOA. And then part 2 is to work out the cosine of q. So just turn into the other triangle. So this is q. Careful again, this is opposite adjacent hypotenuse. Just be careful with the orientation. So adjacent over hypotenuse, so it's going to be 3 over 3 root 5. And that would simplify down a little to make it just 1 over root 5, like that. So that's part A of the question. Part B of the question is asking us to kind of build upon this to work out the quantity cos p plus q. So you should recognize that as being in the format of one of the addition formulas. So turn into the formula sheet, expanding this. Remember the formula sheet's got A's and B's on it. Expanding this, so according to that formula sheet, you would get cos p cos q. Be careful because in the cosine addition formula expansion, this plus becomes a minus. So then it's going to be minus sine p sine q, like this. So these two guys we've already got. We worked those out in the first part of the question. These guys we don't got, so we got to work those out. So starting to plug in our numbers, cos p is 3 over 5, so 3 over 5. That's multiplying, remember, to the cos q, so I'm just going to use a bracket to separate those, so it's 1 over root 5. Should be, if we get these right, we'll get similar denominators, because the sign in SOHCAHTOA is also over h, like over hypotenuse, so that's a good way to judge it. So sine p, going back to the p triangle, opposite over hypotenuse now, so opposite hypotenuse, so it's 4 over 5. 4 over 5, so notice that matches that denominator, so that's a good sign. And then the sine q value, opposite 6 over hypotenuse, 3 root 5. So it's going to be 6 over 3 root 5. 3 root 5, like this. Okay, so it's just really a numeracy thing now. We just kind of need to simplify this down. So multiplying our fractions together, 3 times 1 is 3, 5 times root 5 is going to be 5 root 5. And then this guy here becomes 24. You could simplify this one first actually, or do it afterwards. Either way would be fine. So this would be 24 over 5 times 3 is 15 root 5. We want to get them to have the same denominator, so we can either simplify this one or make this 15. It's probably better to simplify this one. So we get 3 over 5 root 5, and we're subtracting from that. So these are both divisible by 3. So 24 divided by 3 is 8 over 5 root 5. And then we're just totaling these together. So 3 minus 8 is negative 5. So it's going to be negative 5 over 5 root 5. Why would they just love the 5s, don't they, in this question? So that will simplify a little bit further because you can divide top and bottom by 5. So it becomes minus 1 over root 5. And that is the final answer for question 4. In question 5, we're told that this quadratic equation has got equal roots, and we're asked to find the possible values of p. So equal roots means that the discriminant is equal to 0. That's really another way of saying one root, so equal to 0. So we need to make our discriminant. Good practice to explicitly write down your a, b, and c values. So the a value is 2. The b value is 3p minus 2. You can either use the bracket there or not. The c value is everything that's not the a and the b value, so it's the number or the term on the end, so that's going to be just a p. So we want to start building up our b squared minus 4ac, and because we're dealing with equal roots, one root, we're setting that equal to 0. And the clue is in the question, because if it was greater than 0 or less than 0, so 2 roots or no roots, it would be worded find the range of values of p, not find the value of p. So we're looking for values, p equals something. So plugging in our values for a, b, and c. So remember, you're squaring the b values. So that's 3p minus 2 all squared minus 4 times the a value, which was 2, and the c value, which was p. And remember, we want p's in here because we're trying to solve for p, so we need an equation that's got p's in it. This bracket to square, you would need to either do very carefully, or better still, write the bracket twice just to be careful with that. 4 times 2 times p, that's going to be, I was going to write 4p there, but that's going to be 8p, so minus 8p equals 0. Expanding your brackets, you're going to get 9p squared. You're going to get a minus 2 times 3, so it's 6 minus 6p, and another one of those. So 2 minus 6p's to give you a minus 12p. So I've just done that quite quickly, but just be careful with the work in there. Minus 2 times minus 2 gives you plus 4, and then minus 8p on the end. So this is a point where you can kind of tell if you've done it right, because we're going to form this into a trinomial. And if the trinomial does not then factorize, we can kind of know that it's not right. So minus 12 minus 8 is minus 20p, plus 4 equals 0. So generally no one loves factorizing trinomials. This one is particularly nasty looking because of the 9 in front. But if it does factorize, it kind of validates you've done it right. And if it doesn't factorize, you've probably done something wrong to this point. So yeah, this one is a little bit tricky. I think this would factorize, let's check this, with a 9p and a p and a 2 and a 2. Not easy though, use whatever method you use to factorize to get that. So these two multiplying would give you an 18, that would give you a 2p, and they can be combined, 18 and 2, to make a minus 20. So to achieve that minus 20, we would need the minus minus, and also the minus times the minus gives you the plus 4. So just separating these into two little equations, two little linear equations, 9p minus 2 equals 0, and then p minus 2 equals 0. Second one you can easily solve to get p equals 2. This one you'll get 9p equals 2, so you still need to divide by 9 to get p equals 2 over 9. So those are the two values we're looking for p. In the next question, question 6, we're asked to integrate this expression, this function here. So notice that the second term is in a non-integratable form, but it's a very familiar non-integratable form. So the square root is the same as a half power. Probably done these like a million times, so pretty standard question really. This is going to become the integral of 2x to the 5. Remember, don't integrate that first term yet, even though, because we're going to work on the second term. Even though it is integratable, don't do it yet, because we're not integrating at this point. We're just using the indices rule to make that a 1/2 power, to make both of our terms integratable. Now we can go ahead and integrate. It's a really common mistake that students want to integrate that term while still working on the indices rules for the other term. So these are both in the form to use the power rule, so we can just increase the power by 1. So 2x to the power of 6 over 6. Increasing the power by 1 on the x to the 1/2, a little bit tricky, but adding that 1 is a 2 over 2, so it's 1 over 2 plus 2 over 2, which is 3 over 2, or 1.5. You want to use the fraction though, 3 over 2. Really, really common half power, so you must have made 3 over 2s a million times before, and then you're dividing by the 3 over 2 like this. Those are not quite fully simplified, so you need to simplify them. This fraction will divide top and bottom by 2 to become x to the power of 6 over 3. Second one's a little trickier. You're doing 6 divided by 3 over 2. Dividing by a fraction is like times and by its reciprocal. In other words, if you flip the fraction, so this is really 6 times 2 divided by 3. 6 times 2 is 12, divided by 3 is 4. You could do that as a bit of side working, but eventually that's going to become a 4x to the power of 3 over 2. The powers are both positive, so we can leave those. We don't need to flip them back into a fraction to make them positive. So that's the final answer for that question. In part A of question 7, we're asked to evaluate this quantity with the logarithms. That's fairly straightforward, quite a routine log question. Part B is a little bit weird, to be honest. Never really seen a question quite set up like this before. It's to do with the graph of a log function, which is definitely going to catch a lot of students out. But it's a low mark question. I think it was just 1 mark. So not the worst one to miss. I imagine a lot of people will have missed this one. Anyway, we'll get to that one in a moment. Looking at the first one, so question 7, part A, there are no numbers in front of our logs. If there were, then we would have to deal with those before we combine the logs. We can just combine them based on the plus in the middle. So this is going to become log to base 2. Because of the plus, we're going to multiply these two things together. So it's log base 2, 5 times 1 over 40. We can just start working on that 1 over 40 just to, the 5 times 1 over 40 just to simplify. So that's literally going to become 5 over 40 like that. And then I would just go ahead and probably simplify that down. They both divide by 5, so that's 1 over 8. This is, I mean, you would get marks for that already. This is possibly the part where potentially this could go a little bit wrong, but just think of this log rule. So it's normally the second log rule that basically says if you've got a log with a divide, you can split that into 2 logs with a minus in between. Just like having a plus in between going to a times here, it's a divide goes into a minus, or a minus goes into a divide. So this is kind of using that log rule backwards from how it's normally used, because you normally have 2 logs with a minus in between and you combine that into 1. This time we're splitting it apart into 2. So this is going to become log to base 2 of 1, but importantly it's minus log to base 2 of 8, okay? Hopefully that makes sense. Just think of it like this. If you had these two, you could combine those using that log minus rule into that, so that goes both ways. This time we've split it apart. Log to base 2 of 1, well remember what a logarithm is an exponential backwards. It's like the inverse of an exponential. So what this is really asking you is, what power, what exponent, exponentials are powers, exponents, what power goes on a 2 to make a 0? No, sorry, it goes on a 2 to make a 1, and the answer is 0. So the answer to that is 0. But the answer is 0 because 2 to the power of 0 gives you 1. So we're trying to pick off the power in these questions. Similarly for the second one, log base 2, 8, that's just asking you what power goes on a 2 to make an 8. So 2 to what power gives you 8? Well, that's 2 times 2 times 2, 2 cubed. So the answer there would be a 3. So the answer to this is just 3, not log 3, just 3. So the final answer there, 0 minus 3, is minus 3. So that's the answer for the first part, part A. Part B is a little bit of a sketchy question. So the way you would really need to go about this is to be aware of what the graph of a log function looks like. It is in the course, you should definitely know that, but it is quite obscure. Most students tend to forget what it looks like. An exponential graph goes like this. A logarithm graph is the inverse of that, so it should be the kind of mirror image of that, and it mirrors it by being really close to the y-axis here, and then it kind of does something a little bit like this. But the important thing is that on the log graph, so this graph here would be like y equals log to base 8 of a, or something like that. The important thing with this graph is it goes through this point here at 1, 0, whereas the exponential graph goes through the point at 0, 1. We're not worried about the exponential, I was just showing you that for comparison. But if you think about the question, it's asking where this log graph is negative. Negative, remember, means the part underneath the x-axis, so we're focusing in on this part of the graph. But another feature of the log graph you should be aware of is that it never crosses over the y-axis. So that means that it's going to get closer and closer to the y but never cross over it. So the only values, and in our question I suppose actually I should be careful, this was really the a value, not the x value. In our question we want the values where it's negative, well it's all the values in here. So it's all the values between this point, which is 0, and this point, which is 1. So we just want to capture all the a values between 0 and 1. Slightly tricky question that to piece together, but it is only a 1 marker. Question 8 I would describe as a full stationary point question, in that they're asking for the coordinates of the stationary points of that function. So coordinates meaning full xy coordinates, and also they're asking for the nature of the stationary point. So it's like the full deal, like the most things you could be asked for really in a stationary point question. So stationary point's a curve where the derivative f dash x is 0, so we need to start by differentiating. These guys are all in a differentiable form, so we're straight into our derivative. Just using the power rule, so that becomes 3x squared plus 6x minus 9. So probably need a little statement at this point, something like for stationary points, f dash x equals 0, something like that. Then we're just going to go ahead and take our derivative, f dash x, set it equal to 0, and try and solve that equation. So if we've got this part right, then it should be that in the next step or two we can factorize, and if it does factorize, it probably tells us that we've got it right so far. Notice there's a common factor there of 3, so you can either pull out that common factor, or better still, just divide all the terms by 3. That just gets rid of the numbers, you don't need a bracket, and it just makes it look a little nicer. So now we've got trinomial equals 0 quadratic equation. We're hoping this will factorize. It looks like it will. So an x and an x, we're going to need a 3 and a 1. and a positive 3 and a minus 1. Okay, so then just separating these into two little mini equations, we're going to get x plus 3 equals 0, x minus 1 equals 0. The second one would solve to give you x equals 1. This one would solve to give you x equals minus 3. Sometimes in stationary point questions they'll ask for only the x coordinates, but in this question they're asking for the full coordinates, so we do need the y coordinates. The y coordinates can be a little bit cumbersome because you've got to, plug these values in, but let's just go for it. So I'll do the easy one first. So when x is 1, we're going to get y, which is, remember, your f of x value, by plugging the 1 into here, back into the original function. Be careful not to put it into the derivative. So it's going to be 1 cubed plus 3 times 1 squared minus 9 times 1. Wow, it's horrible, but you just got to go for it. So it's 1 plus 3 minus 9 plus 5. So that looks to be kind of 0-ish, I think, to me. Yeah, 0. So that point is going to be 1, 0. Then we'll do the other one. So when x is, what was it, minus 3? That one's a little bit uglier, isn't it? So we're going to get y equals, just going through the same thing, plug in the minus 3 in here. So minus 3 cubed, and this is non-calculator as well, yuck, horrible. So 3 times minus 3 squared, just be super careful with these, 9 times minus 3 plus 5. Might not be too bad because I think some of these are going to cancel. So minus 3 cubed is negative 27. When it's a negative and an odd power, it goes negative. Minus 3 squared is 9, positive 9, times 3 is positive 27. So they're going to cancel. Minus minus give you a plus, so it's going to be plus 27. Wow, what's up all the 27s? Plus another 5. So these guys would cancel. 27 plus 5 is 32. So that full coordinate there for that stationary point is x was minus 3 and y is 32. Okay, so we've got our stationary points. We need to determine their nature. In other words, what type of stationary point are they? Minimum turning point, max turning point, point of inflection. If you understand these polynomial functions well, you would already know just by looking at the function what the shape of the graph is and therefore what the points are, but you do need to show it formally. So either using the second derivative test or probably more commonly as a nature table. So I'm just going to set up one nature table because I don't believe in two tables. I think that's the most crazy thing. So just one big table, because after all, a nature table is a mini sketch of the graph, right? So the graph's continuous, so the nature table should really be continuous, in my humble opinion. So looking at your two stationary points, minus 3 and 1, remember to get those in numerical order. So minus 3, 1. Choosing numbers to fill in your table in the correct position, but choosing smart numbers, right? Because we need to calculate with these. 0 is fine for a polynomial function. I'm going to use a 10 here, and I'm going to use a negative 10 here. Nothing wrong with using those values, despite what your teacher might say. Anyway, we need to put in the derivative rule, so f dash x, and then finally the shape or the slope or whatever you call that final part where we're going to basically draw stick diagram of the graph. That's essentially what we're doing. So remember, at the stationary points, the derivative is 0. You can put those in. Start with the 0. Maybe that's an easy one. We're plugging it into the derivative. That's going to be f dash 0, which is going to be 0, 0, minus 9. That's going to be negative. The nature of these cubic functions is that they normally alternate. So it should be plus, minus, plus, but we better check it. If you put a 10 in there, you would get 10 squared times 3 is 300. Plus 60, I mean, it's like super positive, so that's clearly going to be positive. If you put a minus 10 in, you're also going to get 300 here. Again, that term is going to dominate the expression, so you could work out carefully, but it's also going to be positive. That's why it's good to choose smart values and not choose numbers, for example, like minus 4, which would be a really poor choice of value. So positive goes like that, then 0, then negative, then 0, then positive. Keeping in mind that this is a mini sketch of the graph, that means the graph in reality goes something like this. It's a curve, it would be a curve like that, and these are your two stationary points. So you can see that this one here is a maximum turning point, and this guy over here is a minimum turning point. So just associating those to the correct point. So this is the one at minus 3, so this one here is a maximum turning point. And the other guy, 1, is a minimum turning point. So 1, 0 is a minimum turning point. Question 9 is a graph transformation question, but it is a tricky one, and it is tricky because it involves not some general polynomial type graph, but a log graph, and it's referring to the inverse. So a few things you need to know there in addition to graph transformation. So they're asking us ultimately to sketch a graph of the transformation f to the -1 of x -1. So first of all, you need to know what this graph looks like, and then you need to think about that on the end as well. That -1 is not the worst thing. You should really know what that does to a graph, i.e. moves it down by 1. So we might want to do this in 2 stages. First of all, sketch this graph, and then sketch this graph. This will definitely catch a lot of students out because exponential and log graphs are quite a minor part of the course, and a lot of people don't really know them or they skip over them. But this is a general shape of a log graph. They always go through the point 1, 0. They've highlighted another point there, which means we need to get that other point onto our other graph as well. So the inverse graph would be an exponential. It will be the graph of f of x equals 3 to the power of x. It goes through the point 1, 0. So that point there. And a general principle between a graph of a function and its inverse is that if this point 3, 1 lies on the function, the point 1, 3 would lie on the inverse. So we know that the point 1, 3, so 1 along, and then like 1, 2, say 2, 3, try to figure out where that point would be, somewhere there. So let's say that's the point 1, 3. So that's just a general principle, and both of those points need to lie on our exponential graph. So that inverse graph, f to the -1, the exponential graph is going to go something like this. I think I'm going to move that point. It didn't seem quite right. So that point would be in like somewhere in about there. It's not quite perfect, but in about there. So that would be the point which is at 1, 3. And this would be the point which is at 0, 1. This is still not what we want, but we need this on our way to getting what we want. So this would be the graph of y equals f to the -1 of x. In other words, this would be the graph of the inverse of this function, and you just need to know that that's the shape of the graph. That's what an exponential graph looks like, and that's what a log graph looks like. So if you drew that, you'll probably get a mark already. That's this part. This part just moves that graph down by 1. So we're just moving these key points down by 1. So that point's going to get moved down to there. This point's going to get moved down so that it's just, well, 1 lower. So somewhere in there, I guess. The graph will still be the same shape. So it'll almost basically be kind of like parallel, like a curved version of parallel to the original graph. So it's going to go something like this. It'll go through that point. It'll go through or close to my other point, and it'll be something like that. So I'll just move this point down. My points aren't quite in the right place because I did it real quick, but that would be the graph you're looking for. So this would be the graph of y equals f to the -1, the inverse of f of x -1. So shifting the graph down by 1. Tricky question, that one. I suspect a lot of students will have found that quite difficult. In the first part of question 10, part A, we're given this polynomial function and we're asked to show that x plus 5 is a factor. So pretty standard polynomial question, other than the fact that it's a quartic function. That does and doesn't really affect things. I mean, in terms of the synthetic division, it's going to be the same. So to show it's a factor, we're going to set up a synthetic division table. Just remember you're picking out the coefficients. So it's a 1 next to the 4, so it's a 1. And then a 3, watch out for the negatives, a -7, and then a 9, and a -30. Because it's x plus 5 that we're trying to show as a factor, we need a -5 outside our table. And then just going through the numeracy, so pulling down the 1, multiplying these together, so that's a -5. Adding them in the columns, so 3 minus 5, or 3 plus minus 5 is 3 minus 5, which is -2. Multiplying again to get a 10, this would be a 3, this would be a -15. Remember, we're looking for a zero remainder because we're told in the question that it is a factor. It's shown that it's a factor, so it is a factor. Adding those together, we're going to get a -6. Multiplying these would give us a +30. So we do get the zero remainder that we were hoping for. So in part A of the question, that's us done. You might just want to make a statement like, since the remainder is 0, x plus 5 is a factor. Cool, so that's the first part of the question, quite straightforward, kind of impossible to get wrong, right? Because if you don't get the zero remainder, then you know that you need to redo the table. Part B of the question is to solve this polynomial equation. Polynomial equations have to be solved by factorizing, so we now know that x plus 5 is going to be a factor. but we need to get the other factors as well. So we're going to need to fully factorize our polynomial. So notice that we've got 4 terms here instead of the usual 3. That's because it was a quartic function. So let's start building up the factors. So maybe I'll just do this over here. So we now know that x plus 5 is our first factor. And to get the other factors, we are using this quotient part. So this is going to be a 1x cubed, not an x squared, as it usually is. So it's an x cubed minus 2x squared, and then plus 3x minus 6. And then we're going to have to factorize that guy as well. So you could, if you wish, just put that equal to 0. That's basically that guy there and that guy there are the same thing in a factorized form. And we just need to keep going to get this factorized to then allow us to solve the equation. But because this is a cubic function, if it was a quadratic, we could just go straight into 2 brackets. But being a cubic, we need to do synthetic division again. So we have to set up another table, unfortunately. And the challenge really is the fact that we don't know what the factor is this time. So set up your table, so a 1, a minus 2, and a 3, and a negative 6. The way this works is kind of by inspection. So the only thing we know for sure, the factor, the number that's going to go outside is going to be, can divide into the n number. So the 6 on the end, the factors would be 1 or minus 1, 2 or minus 2, 3 or minus 3, 6 or minus 6. There's quite a lot there. It's quite a mean question. So I actually did this one earlier and it does come out to be 2, but you would need to try 1. That wouldn't work because you wouldn't get a 0 remainder. Minus 1 doesn't give you a 0 remainder. If you try 2, I think this one gives us a 0 remainder. Let's just check. So that would be a 2, that would be a 0, that would be a 0, that would be a 3, that would be a 6, and that would give you a 0. So I'm just saving a bit of time by not doing the 1 and the minus 1, but the 1 and the minus 1 don't give you a 0. So what does that tell us? Well, it tells us that we've got this x plus 5, first factor. We've now got a 2 outside our table, so it's an x minus 2 factor, remember? That's a plus 2, that'll be a minus 2 in the factor. We've also got our quotient for this table, so that's a 1x squared this time, or just an x squared. A 0x, so that gets knocked out, and then just a 3, positive 3 on the end like this. This is all still equal to 0 because that guy there, and that guy there are all the same thing, just in a factorized form. We're now separating this into 3 little equations. So we get x plus 5 equals 0. We get x minus 2 equals 0. And then we get this slightly odd looking equation on the end, x squared plus 3 equals 0. These look quite familiar. These are sort of linear factors. So that's going to give us minus 5. That's going to give us 2. If you attempted to solve that third one, you would have to move the the 3 to the other side to make a minus 3, and then get the x by square rooting. So you're going to end up with a square root of minus 3. So that's fine in complex numbers if you were taking advanced higher, but in higher there are no real numbers that satisfy that. So that just needs to be essentially abandoned at this point. So there's no solutions in the real numbers for that. So the 2 solutions for this equation are negative 5 and 2. In question 11, part A, we're being asked to evaluate this definite integral. So these terms are in the form that match a formula sheet. So actually integrating is easy enough here, and then it becomes a bit of trig exact values. So this is in an integratable form. We're good to go straight into the integral for part A. So remember that being a definite integral, you'll need to put your result in a square bracket or whatever notation you use. The integral sign goes to negative cosine, so that's going to be minus 5 cos x. You've got to be careful with the plus and the minus in these. Remember, they're different for the derivatives and integrals. They are on the formula sheet. Cosine itself integrates to positive sign, but there's a minus there already, so that'll be still a minus 3 sine x. So that's our integration part. You would get a mark for that already, and then we just need to start evaluating at the limits, which are in radians, of course. So subbing these in, just do it carefully. So subbing in the pi first, the top limit, so it's minus 5 cosine of pi minus 3 sine of pi. This is, of course, a non-calc paper, so you need to think about these values without the benefit of a calculator. So just putting in the values, so no magic to this part. So minus 3 sine pi by 2, like this. Okay, so we can start evaluating these. These values you really need to take off the graph of the function. They are kind of exact values, but they're not the ones from the triangles or the ones from the graph. So thinking about the cosine graph, look, maybe I'll just put a little cosine graph here. So the cosine graph goes a little bit like this. Pi, 180 degrees, is this middle point. Okay, so the middle point on a cosine graph is the lowest point there, so it's at -1. So that's -5 times -1, which is 5. And then the sine of pi, so referring to the sine graph, goes like this. So sine of pi is that middle point again at 180. On the sine graph, that's at 0. So that's going to be -3 times 0, which is 0, of course. Looking at the second one, now we're dealing with pi over 2, so that's 90 degrees. So going back to our graph here, so if you're at 90 degrees, this point here, then you've got a vertical coordinate of 0. So that tells us that's -5 times 0, which is 0. Sine of pi by 2, the sine of 90 degrees, so that's 90 degrees is here. So that top point there corresponds to 90 degrees, pi by 2 radians, and that's the top point which is at 1. So sine of pi by 2, sine of 90 degrees is 1. So that's going to be 0 minus 3 times 1, which is 3, so like that. Okay, then just a little bit of numeracy. First bracket gives you 5, second one gives you a -3, but there's a minus outside, so it's going to be +3, is that right? Yep, and then it gives you a total value of 8. Remember, for this one, you don't need like square units because it's not asking for an area. Even though it's using a definite integral, it's just evaluate the integral. It does represent an area, and that's what part B is about, but that is just a numerical value. Unless it's interpreted as an area, you just leave it as 8. Part B asks us to, I think it was to represent the shaded, or shade on the diagram, the area represented by this integral. I don't have access to the diagram, but I'm guessing it was probably something like this. I'm guessing it was like draw a cosine graph and draw a sine graph, or maybe they were merged together, I'm not quite sure, but essentially the point of this would be, right, if I draw a sine graph first of all, so the sine graph goes like that. So we're dealing with a definite integral between pi by 2 and pi, so it's 90 to 180 degrees if you want to work in degrees. So that's the point there that's at pi by 2, or 90 degrees. That's the point there which is at pi radians. So the shaded area we'd be dealing with for that first term would be that. And because it's 5 sine, this would be like a vertical top point there of 5 rather than the usual 1. On the cosine graph, it would be something similar. Again, I'm not quite sure how they set this up in the booklet. I didn't get to see that, but the cosine graph looks like this. So we're again between pi by 2 and pi. So pi by 2 on the cosine graph is here. So pi by 2. This point is at pi. So we're dealing in this case with that shaded area in there. So I think part B would have been something like that, but part A was definitely like this. So the answer for part A is 8. The answer for part B is something like those graphs. I think part B was only a 1-mark question. Question 12 is asking us to write this trinomial in completed square form, so very standard technique at higher. Slightly tricky, I suppose, this one being a negative coefficient on the x squared, but that's not uncommon. You've probably seen those in past exam papers. Doesn't really change the process any, so we're starting by pulling out a common factor of those first two terms, just the numerical common factor, not including the x, although x would be part of a higher common factor, but just as well pull out the negative 2. So we're going to go -2 like this. That means we need an x squared and a positive 6x in the bracket. This is not the only way to get the answer to this question. There's different methods, but this is the kind of most standard method, I would say. So you don't need to pull that into the bracket. You can do that, but it's not really smart because it's going to make fractions, which is just not a smart way to do it, really. And then this is where the completing the square kicks in. So all we've done there is to factorize using the -2 for the first two terms. We've not yet completed the square. Completing the square is going to happen on the inside of the square bracket. So that's going to be x plus 3 squared, because remember the number in the bracket with completing the square is half of the coefficient of the x term. So half of that number put in the bracket. You then need to take away that number squared. So 3 squared is 9, so we're taking away 9 like this. 7 is just hanging out on the end. We don't need to do anything with the 7. Then we are going to go ahead and multiply the -2 into the square bracket. So we're multiplying it to the bracket and multiplying it to the -9. But when you multiply it to the bracket, because the bracket's got a power on it, you can't multiply it into the round bracket. So we're just going to go -2 times the round bracket just by positioning the -2 in front of the bracket. Then -2 times -9 gives you plus positive 18, and then you've still got the 7 on the end. Notice how we never did anything with that 7. It just hangs out all the way down. There's no need to include it. If you include it in the bracket, you're just going to introduce fractions, which just makes it much harder, makes students make mistakes, because I've seen that happen like a million times. So 18 plus 7 is 25, so the final answer would be like this. Question 13 is in multiple parts that sort of weave together. In the first part, part A, we're making two composites. The second one is just f of g of x. The first one, f of g of pi by 6. To make a composite and then evaluate it at a value, you can either work out g of pi by 6 first and then put that into the f function, or you can work out f of g of x and then evaluate that at pi by 6. It doesn't matter which way you do it. Funnily enough, in the second part, they want f of g of x anyway, so I wonder if that's maybe not the way they intended to do it, but either way does work. I might actually do this part first. So this is just going to be f of the g function, which is 2x. So we're applying the f function to the term 2x. 2x is just going to replace the x in the f function. That's how you do composites. So that's going to give us 2 sine, not x, 2x, 2 sine 2x. Okay, so that's a composite. If you then wanted to work out f of g of pi by 6, you would just go f of g of x, which is this guy here, and put pi by 6 into there. So that's going to be 2 sine of 2 times x, which is now pi by 6, so 2 times pi by 6, like that. And then we need to evaluate that. So this is going to turn into some kind of trig exact values, I imagine. So this will be 2 sine, this is 2 pi by 6, so 2 pi by 6 like that. We'll need to take that a bit further. That's then 2 sine, simplifying that fraction by dividing top and bottom by 2 to get it down to just pi over 3. So this is where, because it's a non-calc paper, this is where the exact values, the dreaded exact values, kick in. So this one's in radians as well. Pi by 3 radians in degrees is 180 divided by 3 is 60 degrees. So if you wish, you can write that as 2 times the sine of 60 degrees if you prefer to work that way. Most people do learn those exact values in degrees rather than radians and then convert. The sine of 60 degrees is root 3 over 2, so that's 2 times root 3 over 2. Those 2's would cancel to give you a final answer of just root 3. So part A, part 1, the answer is root 3. Part A, part 2 is 2 sine 2x. So potentially they're kind of the wrong way around, but that's just the way it is. And then in part B, part 1, we're told that if you put some value p into the f function, so f of p, the answer to that, if you like, the output value would be 1/3. But f of p would just be 2 sine p. So that's what they're telling us as a result. But f of p would literally be just taking p and replacing the x with p. So 2 sine p. Okay, like this. And the question is to work out the exact value of sine p. So these are both f of p, so we can set them equal. So we can say that 2 sine p is equal to 1/3, and then just dividing both sides by 2 to get a final answer, which I will put over here, of sine p equals 1/3 divided by 2, that's 1/6. Okay, so that is the answer for that one. Sine p equals 1/6. Slightly trickier part, the last part, f of g of p. Now we've already got f of g of x down here, so similar to kind of what we did up here, where we put the p into the original f function, we can now put the p into the composite f of g of x function. So this was f of g of x, so that tells us then that f of g of p is going to be 2 sine 2p. Okay, so 2 sine 2p. So we're just trying to piece together the different components that we've achieved in different parts of this question. Then we need to take that further, and it says to write it as an exact value, so need to go a little bit further with this one. So how are we going to do that? Well, this is a tricky part, and it does need a little bit, I guess, of kind of thought or creativity. This is a double angle, and if you think about the formula sheet and the double angle formulas, you could split that sine 2p into 2 sine p, I was going to say 2 sine x there, 2 sine p cos p, it's normally 2 sine x cos x. But remember that this 2 is not part of that formula. This is just sitting in front of whatever we're going to change the sine 2p into. On the formula sheet, that itself becomes 2 sine x cos x, so in our case 2 sine p cos p. I would imagine a lot of students would miss the fact that there's 2 2's there. that's probably designed into the question. It's a little bit mean, to be honest, but that would then simplify to 4 sine p cos p. That's not an exact value though. An exact value is going to be some numerical value like 1/6 or something like that. But if you notice that we've already got the exact value, these two parts of the question are linked together. We've got the exact value of sine p, which is 1/6. So that's going to become 4 times 1/6. We were not asked in any part of the question to work out the exact value for cos p. And this is a difficult part, but we can use the sine p result by setting up a right angle triangle and using SOHCAHTOA and maybe a bit of Pythagoras. So if we allocate this as angle P, remember sine in SOHCAHTOA is opposite over hypotenuse, so opposite angle P would be 1, the hypotenuse would be 6. If we call this side, which we don't know but we need, A, then our little equation, Pythagoras, would be that A is going to equal to the square root of the long side squared minus the other short side squared. So that's going to be the square root of 36 minus 1, which is 35. So that side there is root 35. We want the cosine of P, which is adjacent over hypotenuse, root 35 over 6. Which is a weird kind of looking number, to be honest, but that's just the way that it's come out. Then we can just multiply this all together. So 4 times 1 times root 35, that is 4 root 35 on the sort of numerator. 6 times 6 on the denominator to give us 36. That would simplify down because these are both divisible by 4. So that's going to give us root 35 divided by 9. And I think for that one, that is the final answer. So the exact value of 2 sine 2p is root 35 divided by 9.